everybody. Today, we have a pleasure to have a talk by Professor Ashtekar from Penn State. He will tell us about gravity, geometry, and quantum. Please, 1 hour approximately.
Yes, thank you very much. It's a pleasure for me to speak in this series. And I know that people who participate come from various backgrounds, and therefore I'm going to organize my talk so that in the very first part, I will address a very general issues of quantum gravity that are common to all approaches. And then I will go on to loop quantum gravity as a whole and give a broad introduction, because I know that not everybody is here familiar with loop quantum gravity. And then at this stage, I will stop, and if there are any short questions, I will answer them. And then, of course, I hope that there will be a lot of discussion at the end. I will be available for longer questions and even questions which are not directly covered in the talk. And then I will talk about one illustrative example. Because of time, I can only do one. And that will be a bridge between theory and observations for the early universe up here. And then finally, I will give you a summary and a very broad perspective on quantum gravity, basically joining on to the very first part where I begin. And this is a very broad overview, and I will summarize work of many researchers, and I will not give every name because it will just crowd the slides very much. And this talk is loosely based on a short review that appeared last year with Eugenio Bianchi. It is available on the archives. Okay, so general setting. Now, Einstein's resistance to accept quantum mechanics as a fundamental theory is well known. However, he had deep respect for quantum mechanics, and he was first to raise, in fact, the problem of unifying general relativity with quantum theory. In this paper, in which he discussed gravitational waves for the first time in the weak field approximation, Einstein says, nevertheless, due to interatomic movements of electrons, atoms would have to radiate not only electromagnetic, but also gravitational energy, if only in tiny amounts. As this is hardly true in nature, it appears that quantum theory would have to modify not only the Maxwellian electrodynamics, but also the new theory of gravitation, that is to say, general relativity. Now, more than a century has passed since Einstein wrote, 105 years have passed, but the problem is still open. So one would like to know, why is it still open? Well, physics has advanced tremendously over the last century, and the problem of unification of general relativity with quantum physics still remains open. And the usual answer you get is that there is no experimental data with direct ramifications on the quantum nature of gravity. But if this is the case, then this should be a theory's heaven, right? I mean, there's no experimental constraints, so we should be able to churning out consistent theories one a week, one after another. There should be a plethora of theories, but it's just the opposite. We don't have a single satisfactory theory, a complete theory. And the question is, why is this happening? And from the loop quantum gravity perspective, we believe that the real reason is the following. In general relativity, gravity is encoded in the space-time geometry. Most spectacular predictions, for example, the Big Bang and black holes and gravitational waves, emerge from this encoding. This suggests that geometry itself must be quantum mechanical. How do we do physics if, in fact, space-time continuum itself is quantum mechanical? We don't have a classical space-time in the background. We need new concepts and new mathematical tools. We have to learn how to lift the anchor that tied us to a background space-time and sail the open seas, and we have done that relatively recently. And this is the reason why the problem, we believe, has taken us so long. Now, there are several voyages in progress. These voyages in which we break our kind of knot, the tie with the background space-time, and make the space-time itself quantum mechanical. And then we got non-commutative geometry, twistor theory, Regge calculus, Euclidean quantum gravity, Hosover-Lifshitz, causal sets, asymptotic safety, causal dynamical triangulations, ADF, CFT, conjecture and string theory, loop quantum gravity, etc. And because there is no direct experimental checks, approaches are driven by intellectual prejudices about what are the core issues and what will take care of itself once the core issues are resolved. Now, to most young people, this might seem strange. How can this be? Because, science is supposed to be objective. I mean, certainly when I was young, I felt that science was objective. And in fact, that is what really, it's a science transcends cultures, right? I mean, when I was in high school, I realized that that literature really depends. What one considers a great literature in one language need not be in another language, whereas Newton's laws are universal, no matter what language we speak. And that is what objectivity, transcending culture, is what attracted me to science. However, I think C.N. Yang has given us something very nice, something very clean understanding of this phenomena. And so I, as I just said in the last transparency, that this sounds strange and isn't science meant to be objective. So what C.N. Yang tells us is that taste and style have so much to do with physics. It may sound strange at first, since physics is supposed to deal objectively with the physical universe. But the physical universe has structure, and one's perception of this structure, one's partiality to some of its characteristics, and one's aversion to others are precisely the elements that make up one's taste. Thus, it is not surprising that taste and style are so important in the scientific research. And I think this really is an issue, particularly for quantum gravity, that people should be aware of. So illustrations of this taste and style that C.N. Yang so eloquently explained to us. I'm just giving you two approaches here because of that time limitation, and they are going to be string theory and loop quantum gravity. So in string theory, it was developed really initially by high energy theories, and initially at least, the big issue was always that unification of all interaction. So unification problem was considered as being the central, and so supersymmetry, higher dimensions, and negative cosmological foundations were at the foundation of the theory. And the whole idea was that one should have extended objects and rather than point particles and natural UV cutoff. At the time, supersymmetry had not been seen. There was no signature of higher dimensions, and the negative cosmological constant is not seen even today. But the point was that these somehow it will happen that these things will arise. And again, this is the prejudice that unification is central. We proceed, and then other things will take care of themselves. In loop quantum gravity, on the other hand, this was developed by relativists, and so non-perturbative methods and background independence were central. And it is based on quantum Riemannian geometry, just like general relativity is based on classical standard Riemannian geometry. And because of quantum Riemannian geometry, there is an inbuilt ultraviolet cutoff. So there are some similarities between the two, but you can see that what C.N. Yang called one's taste and prejudices really come into being as to how one approaches the problem. Now, the current mainstream thrust in string theory, and this is really nicely encoded in this article, which is called The Strange Second Life of String Theory by Casey Cole, who was a journalist in residence at the IAS in Princeton. And on that website, you can find this article, and it says, string theory has so far failed to live up to its promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most useful sets of tools in science, both in mathematics and physics, various branches of science, which have in some sense not directly anything to do with gravity. For example, QCD. On loop quantum gravity, on the other hand, the focus continues on the long-standing problems of quantum gravity itself. The problem of time, the taming of the Big Bang singularity, the pre-inflationary dynamics and large-scale anomalies in the CMB, graviton propagators and endpoint functions in a theory without a background space-time. These are conceptually hard questions, and that is what one is doing. So this was the organization, and since it is qualitative, I thought I would postpone the questions at the end of the second part, where I will introduce some more concrete notions. So in the second part, I'm talking about loop quantum gravity. And the idea here is that we need a new syntax. All of physics sort of needs syntax. The syntax for Newtonian gravity or Newtonian physics was calculus. Syntax for quantum mechanics is provided by functional analysis or Hilbert space theory, self-adjoint operators, and so on. And syntax for classical general relativity is provided by the Riemannian geometry. And so we begin with Einstein's outrageous idea that gravity is not a force, but a manifestation of curved space-time. Therefore, general relativity needed a new syntax to talk about curved spacetimes, and this syntax is the Riemannian geometry. In loop quantum gravity, since geometry is a physical entity like matter, the stance of loop quantum gravity is that geometry also should have an atomic structure, should also have quantum mechanical structure, and therefore quantum gravity needs yet new syntax, and that would be to describe geometry, which is a physical entity, in a quantum mechanical way, and that is the quantum Riemannian geometry. To probe this atomic structure, we need a non-perturbative approach. So no background metric, no classical background metric. And this metric, the classical metric, is to emerge on coarse graining. In this spirit, Dirac, Bergman, Wheeler et al. Introduced quantum geometrodynamics. It is a Hamiltonian approach, and a little bit later, Misner, Hawking et al. Introduced a sum or histories approach, using metric as a fundamental variable. Both these approaches were non-perturbative. The dynamical variable is a space-time metric, and that then becomes quantum mechanical. And so there is actually a quantum geometry. But the action and the equations of motion are highly non-polynomial if you use the metric. For example, if I look at the Hamiltonian approach and use the Arnovitz-Misner variables, which is really the metric, the three-dimensional metric of signature plus, 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 and its canonically conjugate momentum, which most of you know is the extrinsic curvature minus the trace of the extrinsic curvature times the metric, the whole thing multiplied by square root of the metric, a square root of the determinant of the metric. That is the conjugate momentum. And then the dynamics is given by, generated, as most of you know, by constraints. And the Hamiltonian constraint, which is the H gravity, the gravitational part of the Hamiltonian constraint, is given by the scalar curvature of this three metric, the determinant to the power of 1/2 of the scalar metric. Epsilon is equal to +1 for Riemannian signature, -1 for the Lorentzian signature. And then this is, of course, nice. This is just polynomial in the metric and polynomial in the momentum. But these factors of Q and the scalar curvature make this Hamiltonian highly non-polynomial in the original, in the basic variables. And then if you look at the metric variables that are actually the equations of motion in the metric variables, that they're also highly non-polynomial. And therefore, in quantum theory, the hard field theoretic issues related to infinite number of degrees of freedom had not been faced systematically in either of these approaches, the Hamiltonian approaches or the sum over histories approaches that was developed by Misner, Hawking et al. The measures and so on remain formal. And this changes dramatically in loop quantum gravity for the following reason. The key idea here, there are two key ideas. The first is really dramatic shift from metric to the connections or the vector potentials of gauge theories. And a contemporary perspective, a new result, also some quite new results and new directions can be found in this in this paper only 2 years ago. The general idea is quite old, goes back to mid-80s, but it is still new insights have emerged recently. And so the idea is to reformulate general relativity as a Yang-Mills theory, but one important difference, and the important difference is that there should be no background metric in the space-time, because the metric itself is a dynamical variable, is going to be a dynamical variable. But the important thing is that in the initial stage, what one does is just really a gauge theory, a connection and its canonical conjugate variables. The phase space is just that of the gauge series, but the Hamiltonian and so on have to be constructed from the gauge theory variables themselves. They cannot involve a background metric. And the phase space is just the vector potential or the connection and the canonical conjugate momentum, as in SU2 gauge series. So both of them have internal indices they take values in Lie algebra of SU2. And now the point is that if there is no background metric, there are very few gauge invariant expressions that one can write down without a background field. And actually, it turns out that you can only write down, if you restrict yourself to the simplest expressions you can write down that are at most quadratic, then it turns out that these are precisely the constraint equations of Einstein theory. Of course, so far they don't look like the ADM constraint equations that I talked about just a while ago, like the ADM Hamiltonian, Arnold-Desser-Misner Hamiltonian, but there is a dictionary which actually takes these very simple algebraic expressions and converts them to the expressions which are non-polynomial in the metric variables. So for example, the Hamiltonian density, which remember was this non-polynomial expression in the ADM variables, now just becomes basically a trace of E cross E dot B. The metric now is a derived quantity. So basically, I have to give you a dictionary which starts from this A and E, Yang-Mills theory, which has never heard of a metric, and construct a new quantity called the metric, the 3-metric QAB, and the momentum PAB, or the extensor curvature, if you like. And there is such a dictionary. And given this dictionary, to obtain this dictionary, to get the metric, one just declares that these Yang-Mills electric fields, which really takes values in the Lie algebra of Yang-Mills theory, if I take its trace with respect to the Pauli matrices, then I get just something which is only three objects, which are just the vector with a I index up here. We just declare them to be orthonormal triads. And thus, Riemannian geometry is emergent. I did not have a metric, but we just introduce it. And it arises from the background independent gauge theory. In the metric picture, then, what about the connection? Well, the connection, the Wilson lines of this connection, they parallel transport left-handed spinors in the solutions to the field equations. And these are just the chiral spinors of the standard model. Thus, we do two things at once. First of all, the equations are dramatically simplified. And secondly, the emphasis on gauge theories bring general relativity closer to the other basic interactions. And then there has been a confluence of ideas, starting from Penrose's spin networks and twistor theory, Newman's and Plabansky's self-dual gravity, and also Yang-Mills theory, the Dirac theory of constraint system and Feynman path integrals, and of course, gauge theories themselves. And that is what led to construction of loop quantum gravity. So how does the quantum Riemannian geometry itself arise? So what we do is we carry out a non-perturbative quantization of a background independent quantization of the gauge theory. So the idea is to import techniques from gauge theories, like, for example, the Wilson loops, and smeared electric fluxes. So we just take a test field, which also has an internal index, and you smear it on two-dimensional surfaces. So you got here one-dimensional line and two-dimensional surfaces. So these are fluxes, if you like. So from Yang-Mills' point of view, there will be just fluxes and Wilson lines. These are the basic variables, and they generate a Poisson algebra on the gauge theory phase space. And that has no background fields, no background metric in particular. And these operators, these observers, these functions in the phase space can be promoted to operators forming a quantum algebra A, just like the Heisenberg algebra generated by the Q and the P in quantum mechanics. So we have a holonomy and flux algebra, and then we look for its representations. In quantum mechanics, we look for representation of the Heisenberg algebra, and that gives us the Schrodinger-Hilbert space, square integral function of Q or P, or the Bargmann representation, etc. But in field theories, if you try to do the same thing, we do have the algebra, we do have fields in the canonical conjugate momentum, but because of infinite number of degrees of freedom, there are infinitely many inequivalent representations. Even if you impose Poincare invariance, these infinitely many inequivalent representations remain. However, in gravity, there was an unforeseen result. And it is really coming because of diffeomorphism freedom, or the background, or covariance, if you like, or the background independence, or covariance that is important, that the fact that there is no background metric. Because of this, it turns out it's a strong enough condition that, in fact, this algebra A admits a unique representation by operators on Hilbert space H, subject to the standard regularity conditions. And infinite dimensional issues are fully controlled. We have got a regular Borel measure, normalized Borel measure, on the space of A of generalized connections. Even in field theory, if you were to work with this algebra in its representation, the representations that we look at, for example, in the fourth theory, which is solvable, the fields are
what happens?
Okay, the fields are really the states are really functions, square integral functions on the space of generalized distributional fields up here. So here also we got generalized connections, and the wave functions are which constitute Hilbert space. They are the square integral functions on this space of generalized functions with respect to a regular Borel measure. There are no background fields such as a metric. We only have a manifold in the background, and therefore we have got diffeomorphism covariance. As we will now see, quantum Riemannian geometry emerges from this setup. Diffeomorphism covariance simplifies the analysis considerably. For example, the expressions of the various geometrical operators that one can write down are simple because there are very few things you can do in a diffeomorphism covariance framework. The framework was systematically developed by a very large number of researchers, and it is as follows. The fundamental excitations of the geometry are one-dimensional. So you probably have heard of spin networks, and that is illustrated here. So the fundamental excitations are one-dimensional. So in space, you can think of as a graph, which is giving you a network. And this graph is going to have nodes, and it is going to have links up here. So the links are labeled by spin 1/2 representation, and that is because of the SU2-Yang-Mills theory. And the nodes have intertwiners, which basically tie up the indices of incoming representations with the outgoing one. So we got this, we can construct these objects, which are spin networks. And the statement is that if you give me such a spin network, then I can construct canonically a function of the connection. How? Well, you just are looking at holonomies, and looking at holonomies of group elements. You look at the matrices in the representations, and then, for example, here spin 1/2 representation up here, or spin 5/2 representation, and then you just tie up all the indices through intertwiners. That gives you a function of the connection. So given a function of the connection, this graph extracts from the connection only the information that is available, that is encoded in the Wilson loop, Wilson lines along the edges of these loops appear, and that is going to be a wave function. And these wave functions are square integrable and with respect to the rigorous measure. So the fundamental excitations of geometry are given by these Wilson lines, and they are a one-dimensional polymer line. And the continuum arises only when you coarse grain a whole bunch of them and take averages, expectation values of various operators, then the continuum metric will arise. On the left-hand side up here is a picture, a depiction of a horizon of a black hole, a manifold with the topology of two spheres, and the horizon gets its area because these fundamental one-dimensional excitations puncture it. And at each puncture, they deposit a quantum of area, and the sum of all these areas then give you the area of the horizon. So spin networks are a convenient basis of states. States are functions of the generalized connection, psi of A, and this is a convenient basis obtained by you taking the Wilson loop, looking at the Wilson lines, looking at the representation, and then tying up the indices with the intertwiners. The labeled node up here, you can think of it as being these nodes. You can think of it as being quantum chunk of space. Volume resides, a quantum volume resides at this discrete nodes up here. And areas are really intersections of these lines. Area of any given surface is given by intersection of these lines with the surface, as here. Here is the surface, and this intersection deposits a quantum of area. So well-defined geometric operators, they're rigorously self-adjoint, like the areas of surfaces and volumes of regions and also lengths of lines. They have discrete spectra, like those of the Hamiltonian, the L squared and the Lz of the hydrogen atom. Of particular interest is the area gap. There's a zero eigenvalue of the area, but then there's a gap. It's not a continuous spectrum, it's a discrete spectrum. And the smallest non-zero eigenvalue is called the area gap. And this is the fundamental macroscopic parameter of loop quantum gravity that sets scales for the new macroscopic phenomena. For example, the maximum value of the curvature and the maximum value of matter density is given by a constant divided by the cube of this area gap. So therefore, they achieve a maximum upper bound. They don't become infinite. So this is really the second part of the talk, which is I just try to give you a very broad stroke picture of loop quantum gravity. Now, some long-standing lessons of loop quantum gravity. So we want to ask, how do you do physics if there is no space-time metric? What is time and how do you speak of dynamics and happenings? Are strong curvature singularities of general relativity naturally resolved by quantum gravity? Are the ultraviolet divergences of quantum field theory naturally resolved? The answers from loop quantum gravity are the following. How do you do physics if there is no space-time to anchor it? Well, matter fields and geometry are both quantum mechanical at birth. Quantum fields propagate on the quantum states of a geometry. So you only have probability amplitudes of geometry, and the quantum fields can propagate on it. And this is really analogous to, for example, electron in a laser beam. If you put an electron in a laser beam, so electron is like the matter field, and the electromagnetic field is the analog of geometry here. Classically, you will think that the electromagnetic field, the laser beam, is just a classical electromagnetic field, and the quantum field, the electron, is just propagating in that classical electromagnetic field. But if you think of the laser itself as being consisting of photons, so therefore you got quantum fluctuations of the electromagnetic field, and then the electron would feel not only the mean value, laser beam is a coherent state, it is a sharp mean value, the electron feels not only the mean value, but also the quantum fluctuations. That is what happens to the matter in the geometry. What is time and how do you speak of dynamics or happenings? Well, here is a picture. Previously, what I talked about was only the canonical picture. Here is a path integral picture. So here is a spin network, and you got an evolution of the spin network. So we have one spin network here and another one here. The new spin network here is an additional, something additional is happening up here in the new spin network. And so the question is, how do you calculate the transition amplitude? So you look at a two simplex. The two simplex, basically, you can think of the face here as being evolution of this edge, line here as being evolution of this node. But the point is that new vertices can be produced, and this is really the quantum dynamics, and that is why you might have different area, different volume in the initial state than in the final state. So you get transition amplitudes that way. So how do you define time and how do you speak of dynamics? A matter field can serve as a relational clock with respect to which other fields evolve. And the example of happening is a new node that is creation in the chunk of volume that can be created or destroyed. Our strong curvature singularities of general relativity naturally resolve in quantum gravity. In cosmological models, black hole, and also some black hole models that have been considered so far, space-like strong curvature singularities are tamed. In cosmology, not just the Big Bang, but also big rip and sudden death singularities. What about the ultraviolet divergences? Here, the situation is not as clean-cut. There are some concrete results, particularly due to Thiemann, on regularity of matter Hamiltonians in loop quantum gravity with respect to ultraviolet, but we do not know how to systematically relate those results to effective field theories. So these are the roughly half the talk. So I stop here, and if there are questions, I would like to take them now.
Okay, questions, please.
Can I ask a question?
Oh, yes, please, Igor, ask a question.
So you said that you start from a classical manifold and then
That's correct.
consider a connection. Is it true?
Yes.
So therefore you have background as a classical manifold.
Yes.
Therefore, in this sense, your theory is not completely fully quantized.
Yeah. We start in the classical theory that way. That is how the classical manifold is built up here. But when you go to quantum theory, then the statement is that you have got these abstract two complexes. So we should distinguish between what I started so far. I started with the classical theory, but when I arrived at quantum theory, what you have is two complexes like that. Not a four-dimensional space-time. Four-dimensional space-time would be an approximation in the quantum theory.
So you start from a classical manifold to fixed topology.
Classical manifold fixed topology in the classical theory, yes.
You consider four-dimensional space or sphere or what?
Yeah, it's a no. It's a again. Your question, I want to emphasize. If you're asking the question at the classical level, yes, we start.
No, I'm asking about the quantum case. In quantum case, you have
quantum theory. What you have is just these two abstract two simplexes. What you have is really abstract spin networks, graphs. They are not necessarily embedded in any space-time.
Okay.
Okay. They are not necessarily embedded in any space-time. Okay. Shall I go on?
No, excuse me. There are two more questions. The first question is from Philip Mannheim. Philip, please ask your question.
Yes, good morning, and thank you for this nice introduction. I wanted a question about the gap parameter delta. One is, why is it universal? Two, why is it actually non-zero? And three, wouldn't it lead you to an enormous cosmological constant?
So I didn't understand the third one. So there's a gap that comes up because there is a specific Hilbert space. That Hilbert space has a fundamental discreteness that is built into it, and you look at the areas. So, for example, area is really, as I said, arises because you've got a surface and there is a deposit of a quantum of area. So, therefore, if you can have no intersection, no excitation of geometry at all, then the area will be zero. But as soon as you have excitation of geometry, then the first excitation of geometry will give you a quantum of area, and that is why there is a discreteness. Right? There's no continuum thing. The area is really obtained by eigenvalues of this spins up here, which are deposited on the two-dimensional surface. Then the second question was about.
Okay, so that will make it both non-zero and universal. That's fine, but why wouldn't it then lead to an enormous cosmological constant?
Because it's an area. It has nothing to do with the cosmological constant.
No, but it's the scale. It's the scale of the theory, and the cosmological constant goes like the inverse of length scales.
Just because there is a scale doesn't mean that, I mean, cosmology, this is a kinematical construction.
Oh, okay. So
Cosmological
when you
constant.
say that it sets the scale for new macroscopic phenomena, somehow it doesn't set the scale for the cosmological constant.
No, it does not. Right. So you can do this with lambda equal to 0. You can do it with any value of lambda. The value of lambda is not tied anyway directly to the area gap.
Oh, okay.
Okay, there is one more questions. This question is from Rifal Khan. Please ask your question.
Hi, I have two questions. First is, what in loop quantum gravity, what exactly is a state? And the second question is, like, given a state in loop quantum gravity, is there some sort of an approximation with which I could get a Wheeler-DeWitt state as a solution to the Wheeler-DeWitt equation in terms of a superposition of geometries?
Right. So a state is really, basis of states is provided by the spin networks up here. So if you like a space, I mean, mathematically, there is a notion of generalized connections, and a state is a functional, a complex function of a generalized connection. And if you like, it's like a distributional connection, which is square integrable with respect to that measure that I told you about, which exists rigorously. Then the second question was about the, can you say the second question again about the Wheeler-DeWitt theory? No.
Yeah, so I have a superposition of geometries, which is a solution to the Wheeler-DeWitt equation. Now, given a state in loop quantum gravity, is there some sort of an approximation which one can do to get a Wheeler-DeWitt state?
It's the other way around. Namely, loop quantum gravity is considered to be fundamental, and the states in loop Wheeler-DeWitt equation, because in Wheeler-DeWitt case, that we don't have fundamental discreteness. So it's only when you forget about fundamental discreteness, then the Wheeler-DeWitt states can arise. So that's a good approximation away from the Big Bang, for example, in quantum cosmology, but not a good approximation before the Big Bang.
Thank you.
Okay. So let me go to the next part of the talk, and the next part of the talk has to do
Yes,
with
please.
loop quantum gravity and the very early universe. So basically, I'm giving you an example of a recent example. So for concreteness, I will look at the inflationist paradigm. It is highly successful as it has been highly successful, but it is not a fundamental theory, for example, like general relativity, rather, as Jim Peebles says, it's a framework on which to hang a theory. So inflation begins much after the Planck regime, where matter density and curvature is about 10 to the minus 11 times the Planck scale up here. And considerable work has happened in loop quantum gravity to expand it into the Planck regime. What happens is that really the Big Bang is replaced by big bounce. There are no infinities, and curvature has an absolute upper bound, which is about 62 Planck length to the minus 2. Therefore, the background geometry remains well behaved. The quantum geometry remains well behaved. The cosmological perturbations that grow into large-scale structure propagate on this quantum geometry. Planck scale issues are faced squarely, and this evolution has been studied by different groups, leading to bridge between theory and observations. So singularity resolution up here, for example, with the Starobinsky potential here. So what I'm plotting up here is really take some region of space-time, spatial region, and we look at the volume of this spatial region, and we look at the scalar field up here. So instead of the scale factor, I'm looking at the volume of a spatial region up here. And so what I'm looking for here is really expectation value of the volume operator in the Starobinsky potential up here. And the Big Bang is really replaced by big bounce in this case, as I will see in a minute. And yeah, and then sorry, something happened which is not right. Just 1 second. Yeah. That's right. That's fine. So what happens is that so I'm plotting here the scalar potential and scalar field and the volume of the universe. And as the scalar field rolls down, the volume of the universe expands exponentially during inflation. That is we saw. But then what happens if you went back? Well, if you went back, then classical general relativity will say that you go down to zero volume and there is a singularity. But what happens in loop quantum gravity is really that there is a bounce. So the Big Bang is replaced by big bounce up here. And the singularity resolution happens also in general cosmological model. So if you go back in time, then the scalar field actually the scalar field actually, the volume of the universe actually undergoes a bounce up here instead of a Big Bang, and the scalar field continues its evolution. So really, there is no Big Bang singularity. Big Bang singularity is actually resolved up here. So what is behind this singularity resolution? What happens is that there is a key modification of Einstein dynamics, and that is captured. I'm not writing the full equation, but that is well captured in the quantum corrected Einstein's equation. For example, the quantum corrected Friedmann equation. The Friedmann equation is in blue, A dot by A squared. This is a scale factor, is given by 8 pi g rho over 3. But now it acquires an extra term because of loop quantum gravity connections up here, quantum geometry corrections up here. And then this rho sub is given by explicit formula, which features the area gap. And when you put the numbers in, it is about 0.41 Planck density. So when that happens, this factor actually, when rho reaches rho sub, this factor disappears. So A dot disappears, and that is where the bounce takes place. And the statement is now that the mechanism is really that there is no unphysical matter that is put for this bounce to occur, or new boundary conditions like in Hartle-Hawking boundary condition. The quantum geometry itself creates a brand new repulsive force in the Planck regime, overwhelming the classical attraction. And this has been understood in the Hamiltonian picture, the path integral picture, and in the consistent histories picture. Matter density operator that has been constructed has an upper bound on the physical Hilbert space, and this upper bound is the one which gives you this rho sub up here. In other words, that is the upper bound at which this bounce occurs up here. And this provides a precise sense in which the singularity is resolved. If you take this area gap up here, the smallest eigenvalue of the area, if you take it to 0, then of course, rho sub becomes infinite. And therefore, it is really the quantum geometry which has this finite area gap, finite smallest area eigenvalue, that really is in some ways responsible for this bounce. And the statement is that in this limit, then the classical and the Wheeler-DeWitt result is recovered, particularly the result that was the Wheeler-DeWitt theory that was talked about just a while ago, based on the metric variables. So there's a documentary which is called The New Meaning of Big Bang, and it is really interesting because in the mainstream cosmology now, the Big Bang refers not to an initial singularity, but to a hot phase in the early universe, say at the end of inflation. And there is a consensus that that's what the Big Bang really means, the new meaning of Big Bang. And it really is something that I would like to sort of talk about. But it is in loop quantum gravity that this big bounce, the idea that there is no really a Big Bang singularity, was first introduced. I think that it's fair to say that this is where it started. And now more and more, there's a new meaning of Big Bang that is being accepted. So why? So the question is really basically that how does this occur? And secondly, why does it matter? Because you can start with pre-inflation and go in the future, but why does it matter? Why do you have to go back and worry about the Big Bang at all? So why does the pre-inflationary dynamics matter? Well, contrary to the widespread belief, the pre-inflationary dynamics matters because modes whose physical wavelength is bigger than the radius of curvature, in the pre-inflationary era, they get excited and populated at the onset of inflation. And then this can leave imprints on the CMB, naturally leading to anomalies at low L's. And therefore that could be observed. So here is a cartoon depicting the qualitative behavior of the modes. So here is time, and here is a length scale, and here are various modes up here, and various length scales. So here is the radius of curvature. Sorry, here is the R. Yeah, here is the radius of curvature, the curvature radius that I talked about up here. So now what happens is that the modes that are born up here normally, this is the general relativity picture. These modes, if you go trace back and go back in time, they all hit the singularity up here. In loop quantum cosmology, what happens is the following. Here is again a length scale, and here is time. And the modes, there are modes whose wavelength at the big bounce up here, the Big Bang is replaced by the big bounce, and at the big bounce, the modes whose wavelength is larger than the radius of curvature up here, those modes actually feel the curvature up here and they get excited. Therefore, when they exit up here, those modes are going to be excited, these modes are going to be excited, and these modes are not excited. Whereas in standard picture, none of these modes are excited. So in the new Friedman-Lemaitre-Robertson-Walker dynamics, in turn affects the infrared behavior of perturbations. So there is a deep interplay between the ultraviolet and the infrared. That's the important thing that I want to say up here, because the modes that are excited up here are the modes whose length scale is larger. So these are the modes which are really excited, but they were excited at the bounce, and that happened at the ultraviolet thing. And therefore, you actually find something, the effect in the cosmology, in the observations of this cosmological spectrum. So are they relevant for observation?
Sorry to interrupt you, Abhay, but can I ask a question if it's okay?
No, please wait until I finish and then ask a question. I mean, I can go back to any transparency because I think I'm running out of time here. So please just wait until the end of this section and then ask the question. So there are effects that are relevant. Are these effects relevant for observations? So in 2018, for example, the Planck results that were put forward, and they said explicitly that if anomalies have primordial origin, then their large-scale structure would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain an anomaly, or even better, multiple anomalies. And then again, in this 2015 paper, they had said that the case of the anomalies is strengthened. So perhaps we can look at these anomalies and see if, in fact, these new effects that I'm talking about actually have an influence on them. So we can look at the CMB observations. The 6-parameter lambda CDM model that is selected by Planck has had tremendous success in explaining all the major features of temperature anisotropies and polarizations of the cosmic microwave background. So here is a picture. Here we got the cosmic microwave background. We're plotting the CLs up here, the amplitudes for each L, and these are the temperature fluctuations, the amplitude. And here we got the angular scale given by YLML up here. So basically, as L decreases, you get longer and longer so L decreases up here in this particular direction. Now, in the universe, one has for this universe, one has theoretical predictions for observables such as lensing amplitude and odd parity black body spectrum as well. So the statement is that we have got all these predictions, not only for the power spectrum, but also for various other observables in cosmology. Now, there are anomalies. However, CMB data also exhibits anomalies, and you can see up here that the power spectrum that is actually the best fit power spectrum that is given to us. And you can see here that the observations were got a power deficit at low L's up here. And these anomalies, they are called anomalies. And there's a large scale power anomaly, and there's also an anomaly that goes under the name of lensing amplitude and optical depth anomaly up here. So the large angular scale C theta up here observationally, they are really suppressed up here. So here is the Planck data, and here is what is predicted by theory. So you can see that here we have got at large scales we have got a lot of power, but in the observations we actually do not see that. And here for the lensing amplitude and optical depth anomaly, basically you can see that the whole analysis starts by assuming that the so-called the lensing amplitude is equal to 1. But you can see that this 1 actually lies outside the 68% prediction of the standard of models, the standard CAB model. So again, the perspective on anomalies. So we have these anomalies, and the perspective, as I said, was that in fact maybe the origin of these anomalies lies in some fundamental physics. So what happens in loop quantum gravity? In loop quantum gravity, what happens is that in fact the power spectrum at low power, at low L's, the power spectrum is actually reduced up here. The standard answers that you have got here in usual in the usual analysis is that the power is given by a certain amplitude times the k, the wave number divided by k star, a fiducial wave number to the n to the ns to the -1. And LQC, because of the ultraviolet infrared interplay, this almost scale invariance of the primordial spectrum is violated at a very low scale. So we don't have this up here. The simple law do not have, and we have really a power suppression up here that goes on. So similarly, we got this reduction in the C theta up here. So we have got here 3 plots. Here is the observed plot. Here is a plot which is given by the standard ansatz. That is a Planck model. And here is what happens with LQC. So you can see that LQC improves the situation. It is still not exactly agreeing with observations, but in fact, in terms of errors, it is doing much better for the observed power spectrum here. And similarly, in the anomaly in the AL tau plane, previously in the standard inflationary scenario, what one found was that there was an anomaly, namely the anomaly was, as we just saw up here in the standard model, in the standard model up here, there was an anomaly. The value is AL equal to 1 up here, lies outside the contour that is given by the standard ansatz here. Inside the error path of the 1 sigma contour that is given by the 68% level that is given by the theory. But here, what one sees is that with loop quantum cosmology, with the corrections that happen up here, the anomaly arose because AL was outside the 1 sigma contour, as I was just saying here. That was motivated with the standard ansatz. But this is alleviated because now what we see is that in loop quantum gravity, this is the blue picture up here, So therefore, we see up here that the 1 sigma contour is here in the blue picture, and we see that in fact there is no problem at all. The observed value is really inside the 1 sigma contour up here. And what happens ultimately is really that we got this lambda CDM plus standard ansatz, the standard ansatz that is made for the power spectrum, which is modified by LQC, by loop quantum gravity. What happens is that 6 parameters of the standard ansatz are affected slightly. There are slight differences between loop quantum cosmology and the standard ansatz, the standard model, inflationary model that one has used so far. For most of them, the discrepancy, the difference is very small, is only 0.4%. But for the optical depth, the difference is quite large. It is about 9.8%. So LQC actually alleviates the anomaly because it produces for us a slightly different standard, slightly different cosmology than that is what is given by the standard answers. I mean, still the optical depth there are large error bars in the optical depth, as you can see up here with the, and therefore the statement is that even though the optical depth is increased by 9.8%, we cannot distinguish between them, but the prediction is distinct, and that can be then verified by the future observations, which are going to measure the optical depth a bit better. So let me summarize here, and then we can take questions. Loop quantum gravity starts with a new syntax, and that is really quantum Riemann in geometry, and uses it to address long-standing conceptual issues of quantum gravity related to the absence of a sharp space-time geometry, as well as mathematical problems stemming from an infinite number of degrees of freedom of general relativity. By now, the basic framework has matured sufficiently to seek physically interesting applications. I cannot get rid of this. Okay. In general relativity, the most dramatic effects are associated with the physical and dynamical nature of space-time in cosmology and black holes. At the outset of inflation, the curvature is about 10 to the 55 times that at the horizon of a solar mass black hole. That is why I use the early universe to illustrate the loop quantum gravity implications. I don't have time to do black holes, but if there is interest, I have a few slides in the question period that I can show about the information loss issue and so on, what loop quantum gravity has to say about it. There's an interesting interplay between the ultraviolet and the infrared. Singularity resolution occurs because the ultraviolet corrections to general relativity are introduced by loop quantum gravity. There's a new scale, the curvature radius at the bounds, and the perturbations with wavelengths, which is larger than the curvature radius at the bounds, they receive loop quantum cosmology corrections. And these are corrections to CMB at the largest scales. So there is an interesting interplay between the very large and the very small. And these effects alleviate two anomalies and have led to predictions for further missions, the measurement of optical depth and the tensor modes, the BB spectrum, without compromising the success of the standard parameter. So you can see that there is quantum gravity in the sky in these predictions up here. So therefore, there is excitement about the future missions, and loop quantum gravity people are going to sort of follow that in detail. So to conclude, let me just give a final thought. Because the problem of quantum gravity has been with us so long, and until recently, there was no obvious observational window to test the ideas. Leaders have often made appeals to aesthetics. For example, one finds quotes for eminent thoughtful people like, it would have been a cruel God if to have laid down such a pretty scheme, which is the H space and heaven, Blavatsky and Ted Newman, and have not it mean something deep. So these were the aesthetic considerations. And I just think too many nice things that happen in string theory for it to be all wrong. Humans do not understand it very well. But I just don't believe there is a cosmic conspiracy that created this incredible thing that has nothing to do with the real world. I think that these very noble ideas should be really kind of checked against a reminder from Feynman. And these are the noble ideas that I have really quoted up here. And Feynman told us, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are or what your name is. If it doesn't agree with experiment, then it is wrong. And we got examples from theory, from the history, the steady state cosmology, the elementary particles as chemistry of geometry. That is what was the idea that was proposed by John Wheeler. Very attractive, very beautiful idea, but really we don't see that this being realized in nature. Replacement of local quantum field theory by analytical properties of S matrix theory by Jeffrey Chu. Very beautiful idea, and again, not quite realized in nature. And going back to last century, I'm going back in time up here. Going back to last century, we got atoms as knotted vortices in space. This was an idea that was put forward by very leading people, Lord Kelvin and James Clerk Maxwell, that atoms should really be, that is how actually knot theory was developed, because of these suggestions that atoms might be knotted vortices in space, because at that time they thought that there was ether and so on and so forth. These are very beautiful mathematical ideas, but they don't agree with nature, and at least so far that we know, and therefore they are gone back. And so we should really take that as a precaution, as a lesson in our mind when we look at these future theories of fundamental things like quantum gravity. And here is some supplementary material for people who, for students. There are recent reviews that I already mentioned, and this talk was partly based on that recent review up here. It's a reports on, it's also on archive, reports of progress in physics, but also on an archive. This is a commission article. And there are also chapters by Bianchi, Dietrich, Giselle, Ladda and Varadarajan, Aguirre and Singh and Barbero and Perez in this volume, which was reported in CERN, which is Loop Quantum Gravity, the first 30 years. And for beginning researchers, there is a 75-minute long YouTube video that might be useful. And there is for the cosmological application, which I had to go through a little bit fast, but I'll be happy to answer questions. There's a cover story in the New Scientist that you might like to see, and you can find it in this. So this is all I had to say in the main part of the talk, not in the discussion thing. And so I think I can take questions. And in particular, I think there was a question, perhaps in the chat box already, by Deepak Vaid. So I'm done. Thank you very much. And I'll answer any questions you like.
Okay, thank you very much for your very interesting talk. I see few questions. The first question is from Deepak Vaid. Please ask your question.
Hi, Abhay. My question, I have one question and one comment. My question is about your slide where you showed
Go ahead.
the excited modes.
This one or?
No, the one with the curvature scale and the extra excited modes coming out because of the loop quantum cosmology correction. So I think the very first, yeah, this one.
Yeah, good.
Right. So Mike, what do you mean by an excited mode? Like that's not
good part. So by excited mode, I just mean, thank you. By excited mode, I mean the mode which is not going to be in the Bunch-Davies vacuum. These modes whose wavelength is smaller than the curvature radius remain smaller than curvature radius all the way back to the bounds up here. These modes don't see the curvature. It's a bit like, thank you for asking the question. I was a little bit rushed in this part. So please, other people also, if you have questions, please do ask. So let me just explain this a little bit more. We all know that there's curvature on the surface of Earth. But when I walk, I don't feel that curvature. And the reason is because if I look at the curvature radius, that is much, much larger than my footstep. And therefore, I don't see the curvature up here. And the same thing happens up here, namely, for the modes up here, the wavelength is much smaller than the curvature radius, and therefore they basically don't feel the curvature. Therefore, they are never excited, and they can remain in the Bunch-Davies vacuum, if you like. When they are here, they exit in the Bunch-Davies vacuum state. Whereas modes whose wavelength is larger than the curvature, it's like flying an airplane, a big step up here, they would actually feel the curvature, and therefore they get excited. So therefore, these curvature modes are get excited in this phase up here, and therefore they are not going to be in the Bunch-Davies vacuum at the onset of inflation. They are going to be excited. But as you can see here, these are the modes which are longer wavelength. So longest wavelength modes are the ones which get excited. Is that clear, Deepak?
Yeah, somewhat, I guess. I mean, not 100%. And then I have a comment, which is that you mentioned in the list of ideas that didn't work out, you mentioned the S matrix of Jeffrey Chew. And in that regard, like it's actually incorrect to say that it hasn't worked out, because in the past 10, 15 years, there have been a lot of elements.
No, it was not
of that program.
I mean, the thing is that none of those ideas I want to say are wrong, because they may turn out to be right much later. None of those ideas. I mean, it may be that there is some way of actually realizing many of those ideas. But what I meant was that the progress did not occur following that idea. That idea is not wrong, but the much more progress occurred by looking at just local quantum field theory rather than the emphasis on S metric. That is what was really meant.
Okay. The next question is from Shravan. Kumar, please, Shravan, ask your question.
Hi, Abhay. Thanks for the nice talk. I have 2-3 questions. I hope it is okay for you. So, well, first question is very naive question. So in loop quantum gravity, you kind of get away with the standard quantization, like you have a classical field and then you do a quantization like in the standard way. Like, so you're getting away with this process. Am I correct?
Yes and no, in the sense that one does begin with classical general relativity, but one doesn't. I mean, in a classical general relativity, if you like, yeah, there is a ladder from classical theory to quantum theory, and the statement is that this ladder is still there, but it's just that we look at general relativity in a slightly different perspective from the beginning. We think of it as a gauge theory, and classically it's just a gauge theory. But if I interpret certain quantities in the gauge theory in a different way, the electric field as being a triad, and if I think of the the connection as being a gravitational connection rather than Yang-Mills connection, SU2 connection up here, then I can just look at it as a gauge theory, but then it also happens to be general relativity. There is a dictionary from gauge theory to general relativity. So what one is doing here is really, one is at the classical level, one is reformulating general relativity more in a gauge theory language, and then applying techniques from gauge theory to this, and then finally reinterpreting things for the geometry. Is this clear?
Yeah, but well, then the understanding I have of loop quantum gravity is you start with discrete space-time, and then it is discontinuous, and the large scales, at small scales, it is discrete. So the space-time, nature of space-time is discrete. Is it correct? Then what I'm missing here is how to get this from some action or some kind of quantization. So
okay, good.
This
So
is where I lost.
your understanding is correct, but okay. Indeed, you can think about the current loop quantum gravity is that there are this discrete structure, there are these spin networks, there are these spin forms, and then you take some limit, and then you get the classical theory up here, right? I mean, but the way it was originally done was one really did start with general relativity. One just formulated general relativity as a gauge theory, and then went on to quantization, not using the Wheeler-DeWitt type of ideas, but gauge theory ideas.
But do you have a fundamental field? Well, fundamental field is spin 2, right? And when you formulate as a gauge theory, what does it mean exactly?
That's exactly the point. That's why it was so non-trivial. Namely, that the fundamental theory can be formulated as gauge theory, as a gauge theory. Good, very good. Okay. So let's should be able to. Oh, I forgot. Well, I can write somewhere here. The fundamental theory. So, can you repeat your question again? I'll just answer it. I thought that I had
my question is, when you reformulate general relativity from gauge theory, so what is the fundamental field? Is it spin 2 or you start with what is the classical field?
So let me just use I mean,
Gravity.
since I don't want to make a big jump, since what I presented here was more in the canonical language, so let me make the same canonical language appear. And the statement is that the nice thing is that the fundamental thing, so you can start with the phase space in which I can start with the phase space in which the fundamental thing is really like Yang-Mills theory, A and E. This is really the Yang-Mills phase space.
Yeah.
Completely Yang-Mills phase space up here. And yet, what I can do is I can write down a dictionary, and the important thing is that the equations, however, are not equations that are subject to this, are not Yang-Mills equations, but equations which are background independent. So you write down background independent equations on this. By that I mean is that you don't assume that there's a background space-time. These are the fields to begin with, right? I mean, just that's it. You don't have anything else. And then you write down the simplest equations you can write down, if you like. So the simplest gauge invariant equations or gauge covariant equations that you can write down. And these turn out to be precisely the, okay. And then there is a dictionary. So these equations are basically, well, that's just equation A and E, right? So the first equation you can write down is that gauge covariant E is 0, derivative is 0. The second equation is trace of FAB. You can see that there is no metric used anywhere here. Trace of FAB times EB equal to 0. So trace just means I am taking the internal indices. And the third equation is just trace of E cross, well, since I'm not writing E and B, I'm just writing F, so I can just write down it as trace of EA, EB, F equal to 0. By trace, I mean, again, just I can put here I, J, K, and epsilon I, J, K. That's what trace means. Okay. So these are the simplest equations you can write down, which do not involve any background fields. And then there's a dictionary from these variables to metric and the extensive curvature, if you like, which will say that these are exactly the Einstein's constraint equations. So you can really start in a way which has made no reference to spin 2, spin 1, etc. This really, and what is it that makes it from? Why is this not spin 1 and spin 2? Well, if I had only this constraint, then it would be a bunch of spin 1 fields. But because I have also these additional constraints, additional equations I can write down, and these are all background independent equations, then suddenly it becomes the equivalent to general relativity. So you can write down in the kinematics of gauge theory, certain gauge covariant equations, which turn out to be equivalent to the spin 2 equations of Einstein's theory.
Okay.
This part
This is classically, right?
It's classically. And then what one does classically, right? Which is the non-trivial observation that in fact Einstein's equations, which has a Riemannian metric, etc. That's all put in the background here. There is no, and even spin 1, spin 2 is not there. It's only at the end of the day when you have introduced a metric by starting from these E's and A's that it's a derived quantity, if you like, that metric satisfies Einstein's equations. Okay.
Okay. Okay.
So this is at the classical level. Then the idea is that at the quantum level, if you want to do quantum gravity, you start with this gauge theory formulation of general relativity. And you go to quantum theory as you would in gauge theories, except don't use any background metric. These are the only variables you have. And that is what gives rise to the spin forms. And that is what gives rise to these various diagrams I was writing down up here, the spin networks, or this is an example of a spin form. So here is an initial amplitude, initial spin network. This is a final spin network, and this is a transition amplitude here. So I can write down this in this in the path integral framework, for example. But that is, so to say, in the quantum theory. So I started by rewriting Einstein's equations in a gauge theory formulation, where the metric is a derived quantity, it's an afterthought. The three-dimensional metric is just going to be given by three-dimensional metric QAB, will be given by just trace of, if you like, is given by.
But
Yeah, it's given in terms of this ease.
Clarification. So, even at the quantum level, there is you don't take any background. So that means the nature
Exactly.
of space-time at quantum level is universal.
Exactly. So in the standard, in the quantum level, there's also no
Here-
background. There are no background fields. I mean, you can do perturbation theory, but if you want to do at a fundamental level, there are no background fields. That's exactly right. So what you have is really states of this kind, you know, this spin network kind of thing, this states of this kind. They will be in 3 dimensions, the spin networks. That is a fundamental discrete structure. And Einstein's theory then is a coarse grain approximation.
Okay, here it goes. My next question in the standard, in general relativity, because since you talked about inflation, when we quantize inflationary fluctuations and especially the tensor fluctuations, we choose there is Bunch-Davies vacuum, well, adiabatic vacuum, not Bunch-Davies. Maybe Bunch-Davies you need to quantize all modes, but adiabatic vacuum quantize few modes in the inflationary context. But see, when I understand graviton in the standard picture in general relativity, graviton propagator is different in different backgrounds, and the vacuum is different. I mean, the Bunch-Davies is surely different from the Minkowski vacuum. So there is an effect of curvature on the vacuum you choose, and here you're evading this, and but still
we're not avoiding this at all. No.
Okay.
So there's the effect of curvature. So at low curve, okay. So everything is really done in terms of the spin networks, or if you like, everything is done in terms of these connection variables, which, you know, I don't have to even talk about space-time metric, like, except that to ask physical questions, I would like to construct the space-time metric starting with this connection variable. So basically, as I said, this emphasis on this brings, so we don't talk about the metric GAB or G mu nu, but we talk about these A's and E's, and that brings the general relativity closer to these other basic interactions. But when we want to talk about G mu nu, we can construct it from this A and E, right?
Okay, so analogously, like, okay, this I understand, but how to say, like, you have some in the standard picture, you have spin to mode propagating in Minkowski background and propagating in black hole or de Sitter background. So there is a difference, and how the difference appears here in this picture.
Very good. So the statement would be that there would be a background, if you like, a background spin foam or a background spin network. It depends on whether you do the Hamiltonian perspective or the path integral perspective. There'll be a background spin network like that, which will correspond to, say, Minkowski space. It will correspond to Friedman, Lemaitre, Robertson, Walker space. And then there are perturbations that will be propagating on that.
Okay.
Okay.
Sorry, can I short question? Sorry, if there's time. So my last question is about because you presenting it from just general relativity, but also when you talked about cosmology, you're talking about Stravinsky model, which is R plus R square, and well, you can extend it even further to stellar gravity, R plus R square plus Y square. So surely these gravity theories are quite complicated. Is there a way to formulate these theories as from loop quantum gravity, because R plus R square and
Y so people have done that, particularly the Stravinsky one is done. I mean, you can rewrite it, right? Stravinsky one is done, but the other ones, I'm not completely up to date about all the things that have been done, really. But yeah, the other theories have been. I mean, there's less work for the Stravinsky inflation. Yes, I mean, there's a lot of work in that case. But for more and more complicated theories, there is less work. But Stravinsky part has been done. I mean, that's what one uses all the time.
Okay. So, is there any notion of renormalizability in this?
Renormalizability comes. I mean, the theory is supposed to be finite, right from the beginning. There's ultraviolet regularity because of the fundamental discreteness. The infrared one, you might, if it's a positive cosmological constant, then there is also infrared regularity up here. So I think the renormalization, etc., comes up because it really has to do with perturbation theory, right? I mean, it is not. So the claim is that there is a non-perturbative theory, and that non-perturbative theory has good good predictions. But of course, I mean, one can actually talk about renormalization in terms of talking about this is what people like Bianca Dietrich talk about, for example, by doing more and more coarse graining. At a fundamental level, you will have some fundamental quantum geometry, which is all excited at the Planck scale. And then you coarse grain. And as you coarse grain, you get more and more the renormalization comes in that level. So what one is presenting here, or what one is attempting to present here, is really the theory at the fundamental level. Is this clear, or shall I?
It's clear. It's clear. Thank you, sir.
Okay.
Thank you very much.
Okay, let's go to the next question. Is it correct that Philip would like to ask one more question? Philip,
Yes,
please ask your question.
Yes, it's correct. Yes. I just wanted to make a very general statement about quantum gravity.
Please.
If I just started from scratch, I would say you want to find a path integral where you integrate over a measure of the metric g mu nu and an action which would be a classical general covariant function of the metric. And that's what I would call and if that succeeds, I would call that quantum gravity. Now, it seems to me that the approaches that you've described and that the string theory people have described don't do that, or don't make any connection with that path integral description. There are only two issues that are involved, and those are the things I've done in my own work. One is finding an action which will give you renormalizability, and that turns out to be the conformal gravity action, and finding a measure that will make the path integral exist and not have any unitarity problems. And the answer to that is yes, you continue the measure into the complex plane. And that's a well-defined quantum gravity theory. And what I'd like to know is, why would that not be the obvious first thing to do if you wanted to construct quantum gravity?
Okay. So no, I think that is a very good thing to do. I mean, then of course one has to go and check, if in fact observationally how this particular theory works, both in terms of say classical gravitational wave observations and also other astrophysical considerations, and then that make more and more tests. So I think that's perfectly fine. But I think in this picture, there is actually the idea up here is that in the spin forms, for example, one is actually doing something very similar. One is trying to write down a path integral. And the statement is that one is writing a path integral, but the initial and the final states that you would choose are different. Namely, it really emphasizes diffeomorphism invariance, and therefore the initial and final states are a bit like this thing that is in this picture up here. And I could have better pictures, but it's a bit like in this picture up here in the so the statement is that you've got an initial state, which is a 3 geometry, which is described by this is the initial quantum state described by 3 geometry, and a final quantum state, which is described by 3 geometry. So what one is saying that at a fundamental, I mean, it's really like saying, look at the path integral, not going in ordinary quantum mechanics, not just going from Q to Q prime, where you just chose Q to be a configuration variable and said that that was a fundamental configuration variable, makes sense also quantum mechanically, but say that the initial Q, or the initial configuration variable, is really a quantum geometry, and therefore is given by this, which when coarse grained gives me classical geometry. So initial state should really be psi of Q, if you like, in the usual picture of writing, and final state will be some psi prime of Q, psi initial of Q and psi final of Q. And this psi initial and psi final is written in terms of these spin network states. And what the spin forms do for you is really a transition amplitude, exactly as what you want to do. And then what one shows is that to leading order, it does reproduce, the spin 2 predictions that one has, but it has much better ultraviolet properties.
Okay. Well, thank you. Just let me comment. As regards the observability of conformal gravity, I've so far fitted 138 galactic rotation curves without dark matter and without the 276 dark matter parameters that you would use for 138 galaxies. I fitted the accelerating universe without fine-tuning. That's why I asked you earlier about the cosmological constant. And I am currently working on fluctuations around the accelerating universe, which is where I am at the moment.
So you do not assume cosmological constant? I mean, you have zero cosmological constant yet?
Oh, no. What basically happens is, in a conformal theory, the trace of the energy momentum tensor is zero. And that constrains the cosmological constant contribution. And we call it the cosmic coincidence, but what it says is if the trace is zero, the cosmological constant and the matter contribution are constrained to each other. And you have to work it through, but it turns out that without fine tuning, you can show that the theory must have a deceleration parameter between 0 and -1. For any values of the parameters. That's the constraint. That's just because of the tracelessness of the energy momentum tensor. Yes.
Okay, so I think these are all very good ideas, and that is one of the good things about this particular series, that is bringing in ideas from different pieces. So what in loop quantum gravity people have done is really look at kind of the very early universe, what happens to the Big Bang singularity? How can you get regularized? Can you get rid of the Big Bang singularity and still have no problem with observations in the cosmological sector? So these are the concept questions one is using. I think it's good to have ideas from various fronts. Absolutely true. I mean, it's a.
Are you happy with his answer? Okay, let's go to the next question. The questions from Igor Valovich. Igor, please ask your question.
Yes, thank you very much for the nice talk. My first question is the following. In the standard gauge theory, there is a Lagrangian correction. Do you have Lagrangian in your loop theory?
So in standard gauge theory, what you have?
Lagrangian, there exists.
Lagrangians, yeah, there are Lagrangians.
What about Lagrangian for your loop theory?
Yes, there is a Lagrangian which is written down in terms of connections and their conjugate variables. That is written down. Yes, there is a Lagrangian.
Okay. Second question is there a relation with Palatini formalism?
Sorry, is there any way to?
Any relation with the Palatini formalism?
Which
Palatini formalism, first order formalism in gravity.
Palatini.
Mm-hmm.
Yeah, it is very close to related to Palatini formalism, but it's not exactly the Palatini formalism because the connection here is not the Levi-Civita connection, but more self-dual connection. I mean, it has internal indices rather than just the space-time.
Okay, then you mentioned you could comment from your loop theory about information loss problem for the black holes. Can you please?
Good question. Okay.
Maybe what we could do is if there is interest, I'm happy to do it, but maybe I should take because there's a long story, right? So maybe I could talk about answer other questions and come back to this. I mean, these organizers tell me, because this is a longer issue, not a short question.
Okay. Okay. Next question from Ruka. Ruka, is correct that you still want to ask a question? Please ask.
Okay. Thank you very much for the nice talk, Abhay. And so I have a question actually regarding the coupling to matter of loop quantum gravity, because so if I think about like quantum field theory, we know, of course, we know to couple minimally gravity to matter, or even non-minimally, we know how to do that. But for instance, if I think about loop quantum gravity, a full non-perturbative level, so in this language of spin foam and so on, how would I even, I don't know, just couple any matter fields, even a scalar field like the Higgs, I don't know. to some matter and try to explain the same physics, to usually explain of standard model and so on. So I cannot imagine how to do it, because it seems that we are really treating gravity as on a different level as compared to the standard model.
Yes and no, because I know the statement is that you've got these fundamental excitations of job at a very, there are levels, right? That really at the quantum gravity level, if you look at the Planck scale level, so to say, then the fundamental quantum state of geometry would be really given by some spin network like that. And then the statement would be that you really have, for example, the Maxwell fields, for example, is a gravitational spin network, this gravitational excitations, that's the place where, if you like, microscopic geometry is non-trivial. And so there'll be some of these links, links that I have up here, which might have, for example, this link, etc. At which there might also be an electromagnetic field. So therefore, then these links will carry not only the spin label, which has to do with more to do with gravity here, but also a U1 level, or some other interaction level. So you will have, in other words, the fundamental fields will also reside either on the vertices or on the links up here. That is given to you. So electromagnetic field again resides on these links, and then there are additional quantum numbers. Basically, what one is doing here, where do this 1/2 and so on, where do these labels come from? They are just representations of SU2. So what one has is really holonomy that is going from this node to this node, and one is looking at it in various representations, and representations provide a nice basis to expand out these holonomies up here. So what we'll have to do is to also add U1, for example, to get a Maxwell field up here.
So basically, you are saying that we should also see other interactions, like of standard model, in a different way in terms of this spin form formalism.
On this spin forms, right? Exactly. One would look at them on spin form, and so the work that is done here is, Thiemann has done work a little bit about writing down the Hamiltonians of the standard model using these fundamental building blocks, this spin networks and so on. But it's true that there could be much more work done here. It's a very nice area in which further work could be done. Mm-hmm. Yeah. So the idea is, I've written papers about with Carlo Rovelli and Lee Smolin in the Maxwell case. How you do this description of Maxwell field, and these Maxwell excitations will also live on some of the geometrical excitations, and then there are Maxwell fields. The Dirac fields will live at the nodes again, just like spin 1/2 fields at the moment coupled to gravity, it's live at the nodes. There will be charged Dirac fields that will live here, as well as there could be also neutrinos which live up here, which will not be charged. The scalar field is the one technically most complicated one. But again, Halno Salman and Jurek Lewandowski and I have papers on scalar fields. So the idea is that at a fundamental level, what we have is either spin forms or spin networks, and other fields live on that. But it's true that in terms of calculations, detailed calculations, not too much has been done. Only the principles have been laid out for that. So that's a very nice area for work.
Yeah,
okay. Next question, maybe Masoud Chinchan will ask the questions, because Raif Khan already asked. But,
following question.
Yes.
Yes. In the usual quantum physics, there is a.
Repeat, please, your question.
Can you hear me?
Now we can hear you.
Yes, in the usual quantum physics, there is a Planck constant, and this is the measure of the quantum nature, right? So, right. And this is independent of the dimension of space-time. Right. And we know that it works in 2 dimensions and in 3 dimensions. Now, in this loop quantum gravity, the equivalent is the area grid or area gap, right?
But that area gap also has
Yes.
H bar
So
in it.
this is in 4-dimensional, isn't so?
For space-time.
For space-time dimension. Is that so?
Right.
Now, if you go to 3-dimension, it means 1 plus 2. So of course, area gap cannot be. It should be something like a line gap or line grid. You agree?
Yeah. So there'll be line.
But it changes, because there you will have another new parameter for this is what I understand. So in the 4-dimensional, you have the area gap as the fundamental, let's say, quantum of the space-time. So if you go to the smaller one, like 1 plus 2 dimension, you should have, this is intuitively, you should have to another one which has dimension less. It means like a line gap, right?
Mhm.
Is that so? So what
Yeah.
is the connection between them? Because this area and line gap, they have no connection, at least in the loop quantum gravity, I cannot see. Is there any connection, or one has to, again, to introduce another fundamental quantity for it? This is the question.
Well, I mean, 2+1 gravity is a different theory than 3+1 gravity. So of course, 2+1 gravity will have other fundamental quantities. I mean, for example, Newton's constant has different dimensions in 2+1 than in 1+1, right? I mean, than in 3+1. So you're going to have, so that's the important point up here. And therefore, if I look at, if I change dimensions, then it's not the same quantity I mean, area gap of 3+1 theory is not related, and it has no direct physical meaning in the 2+1 theory. So it's a 2+1 theory is a 2+1 theory. It has, the Newton's constant has a different dimension. And so H bar has the same dimension, but Newton's constant has a different dimension. And therefore you would get, you would again talk about, the analog of the length operator there, and you will get quantization of the length operator. So it's a, I mean, even Newton's constant has different dimensions, right? And
yeah, but Newton, it is understandable. Newton constant has different dimension because of the potential. Potential has different dimension, and then there is R, the distance is the same. So this has, it is true that is analogous of quantum, let's say, Coulomb potential. But here, so the question is, can you formulate the same loop quantum gravity in, let's say, 1 plus 2 dimension?
yes, so that has been done in great detail. In fact, that was,
yes, and then there is no connection. There is no connection between, I mean, quantitative connection between the delta of area gap and another delta of a line gap. There is no connection, right?
right.
Is that so?
There's no, one does not determine the other, right?
Yes. Thank you.
Okay.
Okay. The next questions, one more question from Rifals Khan. Please ask your question.
Thanks for the talk, Abhay. I have a question, like, is there some sort of realization of holographic principle in loop quantum gravity?
Is that a direct holographic principle in the sense of, that the boundary theory is completely equivalent to the bulk theory? But I think you can look at some partial versions of these principle in work of Laurent Friedel. I think I should not say too much about it because I'm not an expert on it. But there is, look up work of Laurent Friedel. Okay. But it's not the same. I mean, it's not that the bulk theory is equal to the, there's a bulk theory is completely equivalent to some theory in the boundary.
So in loop quantum gravity, there would be more information in the bulk that cannot be obtained from the boundary, is it?
Right. There will be, in general, there will be there is information in the bulk which is not. I should just say, at least it's not certainly not readily obtainable from the boundary, right?
Okay, thank you.
Okay.
I mean, I don't know what happens ultimately, so to say, right? I mean, maybe there's some clever ideas that come up, but at the present, that's correct.
Right, thank you.
Okay, I don't see any more questions. Maybe I will ask just one general questions. Do you have some place for fermions, or
Yes.
or do you have some place for supersymmetry? Okay.
Yes. So both of those things have been done. I mean, fermions, as you can imagine, just reside at this at these nodes, right? And as you would imagine, that's what would happen, and that's exactly what happens. I mean, in gauge theories, you can think in lattice gauge theory, you can say that the fermions live. This is a generalization of lattice gauge theory, if you like. It's not a regular lattice. So fermions will reside at the nodes up here, and these will be the gauge fields will reside at the links up here. So there is a fermion. And there are many papers on fermions. And what was the other question about? And electromagnetic fields will also live on the links up here because they are also gauge fields. So fermions, electromagnetic fields, and you had a third question? Or?
Okay. There is one more questions from Ekaterina Izotova. Ekaterina, please ask your question.
Yeah, I wanted to ask if your fields depend on the space-time coordinate. How do you express Lorentz symmetry and your formalism? Do you have it as usual or something different?
No, the fields, I don't know. Okay. In the classical theory and quantum theory, you have to sort of draw a distinction between the two things. In the classical theory, you have a manifold, and then you can talk about the fields depending on those. You can introduce the coordinates, and then fields will have some dependence on the coordinates. You can do that. In quantum theory, the fields, quantum theory at a fundamental level, what you have is the spin networks or spin forms. They're all discrete objects from the beginning, and they remain discrete. And continuum is only an approximation. So things like usual coordinates and manifold picture that you'll introduce will only emerge on coarse graining. Is this answer your question, or maybe you had something else in mind?
Yeah, but Lorentz symmetry, do you express it in your language somehow?
Okay, so there is something called, there's a local Lorentz symmetry, and then there is, in the tangent space at each point, let me talk about Minkowski space. Then a tangent space at each point, you've got a Lorentz symmetry. But in Minkowski space, you also have a Lorentz group acting on whole space-time, which given a space-like plane, it can act on it and give me another space-like plane, which is say boosted with respect to it. But when you come to curved space-times, you don't have that, right? In curved space-times, you don't have space-like planes, so you don't have the notion of kind of space-time Lorentz symmetry. What you have is a notion of local Lorentz symmetry, which is to say what happens in the tangent space at each point in curved space-time. You've got a metric there, and you can talk about the rotations of the tangent vectors, which really refer to space-time, refer to the tangent space at that point. So the statement is that this Lorentz symmetry, which is really acting at points in the internal space, so to say, at that point, that exists. But Lorentz group, which will actually make a boost from one hyperplane to another hyperplane, that does not have much of a meaning already in classical general relativity.
All right, thank you.
Okay.
I think that I answered some question that Deepak White had, and he said, I sort of answered it. So maybe he can tell me what is it that he did not understand or did not feel was fully answered, if he is here.
Yeah, I think what you say, like locality of the Lorentz transformations, like they're right local, but you have your fields, but how do you define locality in your fields language? Expansion like that.
Again, if you're thinking about quantum fields, then fields live either on the links, in which case at a fundamental level, they are not local. In other words, you do not have at a fundamental level, let's talk about electromagnetism. At a fundamental level, you do not have a mu of x field. What you have is holonomics. You have parallel transport operators from one point to another point. You don't have local operator, local. So those local things are said to be kind of approximations that will come when you somehow smear out enough in order to go from the fundamentally discrete picture to a continuum picture. Then those local descriptions will arise. Then you can talk about electromagnetic field. The moment what we have is not a local electromagnetic field, but rather electromagnetic field will be really flux lines of the electromagnetic field. They will be along these lines. So they will exist only. So here is the gravitational field, and fundamentally I don't have continuum. I don't have fundamentally tensor field at a fundamental level. What I have is really these parallel transport operators and things that live at the vertices, if you like, at the vertices up here. So same thing with electromagnetic fields. You can have charged particles living at the vertices. They can have spin, for example, and then you can have a Maxwell field, parallel transport, a particle from one vertex to another vertex, and so on. So it's a fundamentally discrete picture. It's like in lattice gauge series, but here it is not an approximation to the continuum, but rather continuum is approximation to this fundamentally discrete picture.
Yeah, okay, thanks. I understand it better.
Okay, I don't see more questions. Okay, let's thank the speaker again. Thank you very much for your very interesting talk. We have a lot of discussion. Okay, thank you everybody who participate in the seminar, and especially the people who ask a lot of questions. Okay, thank you.
Thank you.